Thank you so much, sir.
Now I'm requesting Ashwini Kumar, sir. Sir, please continue with the session, sir. I'm requesting all the participants. Sir, 1 second.
Yeah,
I'm
I think I
requesting,
can
sir.
start.
Yes, sir. Sir, 1 second, sir,
Okay.
please, sir.
Thank you.
I'm
My speaker actually is creating some problem, but I think at a low voice I could hear you. And in case
Yes, sir,
in
sir.
case of any doubts or wanted to interact, I think I would request the people to post their message in the chat window. Okay, because
Yes,
I think my speaker has some connection problem. Now we will start the discussion. My today talk is on post-quantum cryptography. I thank the organizers for inviting me to deliver this talk during the faculty development program. Professor Anna Naidu Garu and other members for inviting me. So so we will continue the talk. So my discussion for today would be giving a brief intro to cryptography. And I understand from past 2 days that there were speakers who were introducing quantum computing. So I will not deal with those aspects. I will leave the fundamentals of quantum computing, but I will just show 2 or 3 slides on what features of quantum computing are essential towards the post-quantum cryptography. Then I will talk about the 2 popular algorithms from quantum computing, which are Shor algorithm as well as the Grover algorithm. Then we deal with post-quantum cryptography. What is about that? What are the different variants that are there with the post-quantum cryptography? Then also I will deal with quantum key distribution. In the literature, typically PQC has a meaning and quantum key distribution has a meaning. So this comes under the concept called quantum cryptography, wherein which we leverage the principles of quantum computing to safeguard the communication. That's what is quantum cryptography. When we say post-quantum cryptography, it is all about how to defend, how we are going to defend the communications from quantum computers. So these are the 2 different dimensions in the literature. Post-quantum cryptography is all about how do we defend from the threats generated by the quantum computers. Quantum key distribution is about how do we leverage and take the advantage of quantum computing to secure the communications. So these are the topics that I would be dealing in the next few minutes of our interaction. So all of us know that in our day-to-day life, in our communications, online transactions, everything that we do on digital world, we are looking for 3 fundamental principles, which are nothing but confidentiality, maintaining the integrity, and ensuring the proper authentication mechanism. These are the 3 fundamental principles that are behind any security mechanism we require. So fundamental security mechanism, what we have in the digital world is the cryptography. It is through cryptography, people ensure these 3 principles of confidentiality, integrity, and authentication. Since all of us are all from computer science and information technology domain, I don't deal with in detail of what is confidentiality, what is integrity and authentication. We all know those fundamental definitions, right? In any digital world, especially in the literature of cryptography, we all see there are two users or 2 people interact each other on a virtual in a scenario called Alice and Bob. So they are actually interacting over an unsecured and untrustworthy communication channel, wherein which always there is a possibility of having an eavesdropper or an attacker called Eve. So you have always some kind of a threat in the form of Eve, who is always trying to spy over our data, and hence your confidentiality is at risk. Similarly, since the communication channels are unsecured, Eve can modify the communication that is happening between Alice and Bob, and hence your integrity is at risk. Similarly, you have authentication also is at risk in the sense that how to ensure that both Bob and Alice are convinced to each other that the messages that they are receiving are actually from either Bob or Alice, but not from Eve. So how to ensure that? So these are the security goals that what we have. So these security goals are also influenced by securely storing the data, physical security, and ensuring the access controls. So how to protect the alteration of the data from the unauthorized users. And for that purpose, we have key signatures, message authentication codes, etc. and etc. Now, all these are coming from where? They are coming from the fundamental topic called cryptography, which is primarily aimed at ensuring confidentiality, integrity, authentication, and also providing protection against denial of service attack, and also providing protection against monitoring or eavesdropping over the traffic analysis and all that. So a lot of applications of the cryptography are there, and there is a lot of evolution of cryptography from the olden ages to the modern digital world of computers and communications. Cryptography has evolved a lot. So you can find in the literature classical techniques of cryptography to modern techniques of cryptography that are available, and all these cryptography techniques are providing and ensuring security to our communications. Now, but the point is, these cryptography algorithms are broadly categorized into two types of techniques called symmetric crypto systems and asymmetric crypto systems. What do you mean by symmetric crypto system? When a sender is sending a plain text to a receiver, what the sender is doing? Sender is going to encrypt the message with the help of a key. And then once you encrypt that plain text with the help of the key, what you get is the ciphertext. Now this ciphertext would be there in the communication channel, which is the internet or any other untrusted communication channel. At the receiver would perform the decryption, and for that purpose, the same key is used for decryption of the ciphertext. Once you perform the decryption of the ciphertext, what we get is the original text by the receiver. Since we use the same key for encryption and decryption purpose, it is called symmetric crypto system. The obvious challenge of having a symmetric crypto system is that both the sender and receiver should have the same key. So this is the fundamental challenge. So how a sender who is at a different location and a receiver who is at a different location will have the same key? How to ensure that, or how to provide that same key between the two communicating parties? That is fundamental challenge. Is it that always you will have only two communicating parties? Certainly there may be in a communication environment, you may be having n number of entities communicating with each other. So how do I share the keys? So this is the fundamental problem. And hence what the researchers have come out is a asymmetric crypto system wherein which sender will use a key called encryption key for encrypting the plain text, and we call it as the encryption key. And at the receiver, the receiver will use altogether a different key called decryption key, wherein which the KE is not equal to KD. So both keys are different. So I am performing encryption with the help of an encryption key, and the receiver is performing the decryption with a different key called KD. So keys are different, and hence there is no need to exchange the keys like in the symmetric crypto system. So asymmetric crypto systems are solving the challenge that what we have with the symmetric crypto system. But the point is it that asymmetric crypto system are superior to the symmetric crypto system? No, we cannot say like that. Symmetric crypto system has its own advantage. Asymmetric crypto systems have their own purpose. So now the point is, when it comes to asymmetric crypto systems, first of all, how do I have a two keys called KE and KD, wherein which I am going to encrypt with one key and I'm going to decrypt with altogether a different key? So how do I generate such keys? So what is the challenge with the asymmetric crypto system? Generation of these two keys, meaning encryption key and the decryption key, is the challenge. So when you closely observe, You have a challenge with symmetric crypto system called key sharing. You have a challenge with asymmetric crypto system called key generation. So both have challenges. But at the same time, symmetric crypto systems are faster, whereas asymmetric crypto systems are quite slower because of the challenge of key generation. And symmetric crypto systems have the challenge of key sharing. Asymmetric crypto systems are having the challenge of key generation. Now, what are the various algorithms that we have in the literature? When it comes to symmetric, there are several popular algorithms called advanced encryption standard 128, meaning 128-bit AES, 192-bit AES, 256-bit AES, etc. and etc. When it comes to public key encryption algorithms or asymmetric key encryption algorithms, we have again multiple algorithms that we have. Most popular algorithms are like RSA algorithm, digital signature algorithms, Diffie-Hellman key exchange algorithm, elliptical digital signature algorithms. Like this, there are popular public key encryption or asymmetric key encryption algorithms. Now, where is our focus? Actually, we don't actually deal with this of the symmetric key encryption algorithm. Our focus actually is over the asymmetric key crypto algorithms. Now, few seconds back, I said in asymmetric, you have one particular aspect of creating two keys called KE and KD, right? So in this, among these two keys, one of the key which I'm going to use for encryption purpose is always kept it as public, and then the decryption key is always kept it as private. So since I'm going to perform encryption with the KE, which is public, these asymmetric encryption algorithms are also called as public key encryption algorithms, right? So I've said a few minutes back that there are challenges with asymmetric encryption algorithms. So first of all, how I'm going to generate this type of pair called encryption key called KE or a decryption key called KD. For that purpose, if you look at the user or the communicating party member called Alice, is going to depend upon some random number generators. All of us know that whatever the classical computers that they generate, they typically generate pseudo random numbers. But is it that I can take any random number? Certainly not. Of course, I need to depend on a number which are prime numbers. So there are algorithms called RSA algorithm, which actually create from that particular generated numbers two keys called, one is the public key, KE, another one is called private key called decryption key. So now what happens when once you have this key pair for every user in the network, so Alice will have her own key pair of encryption key, decryption key. Similarly, Bob will have his own key pair called encryption key and decryption key, and encryption key would be declared public and decryption key would be retained as secret. Now then what happens? Using Alice public key, anybody who wanted to interact with her can encrypt a message and send it to Alice. So meaning what? For interacting with Alice, now if you see, Bob is using Alice public key, and for that purpose, Bob has sent a message called hello Alice and encrypted with the help of public key of Alice, which is KE. As name itself says, it's a public key and everybody knows, including Bob. Since Bob knows what is the public key of Alice, Bob is able to decrypt the message with the help of public key of Alice and send that ciphertext to Alice. Now what the Alice is doing? Alice is decrypting that particular message with the help of Alice private key, which is called KD. And hence you are getting the message back. This is how our public key or asymmetric key encryption systems work. So for encryption purpose, we are using the public key of the receiver. So in this case, we are using receiver's public key is used for encryption purpose, and receiver's private key is used for decryption purpose. So encryption is with the public key of the receiver and decryption is with the private key of the receiver. This is how it goes. Now, what are the keys of, what is the use of sender's key pair? Now, when Alice sends a message to Bob, now what happens? Bob will become the receiver, Alice will become the sender. Now, Alice will use Bob's public key. So this is how the communication goes in asymmetric communication systems. Now, is it that asymmetric key systems are used for encryption purpose? In such case, why we are going to for symmetric crypto systems? So actually, if you look at in the practical usages, asymmetric crypto systems are not merely meant for just for encryption purpose. Rather, they are meant for creation of the symmetric keys. Few seconds back, we said one particular challenge with symmetric systems. What is the challenge? The challenge is that how do I share the common key between Alice and Bob, right? That is the challenge with the symmetric systems. So how do these common key between Alice and Bob would be shared, right? That is the challenge. Now, our public key encryption systems would help these two communicating parties, Alice and Bob, to exchange the symmetric key. So how it happens? There are algorithms called Diffie-Hellman key exchange algorithms, which are the branch of asymmetric key, meaning public key encryption algorithms, which helps both Alice and Bob to have a common key. Now you observe this diagram. Alice and Bob. Alice is using Bob's public key and Alice's private key to create a common key called K. Similarly, Bob is using Alice's public key and Bob is using his private key to create the key K. Now, please observe here, both keys are same. Now, is there any communication between Alice and Bob? There is absolutely no communication. But instead, Alice knows Bob's public key and Alice have her own private key. Similarly, Bob knows Alice's public key. Bob has his private key. Using them, they are able to generate the common key K, but it is not actually being communicated. That is the beauty of Diffie-Hellman key exchange algorithm. So if you closely observe the literature of cryptography and read the algorithms of symmetric encryption algorithms, asymmetric encryption algorithms, so people would really enjoy the beauty of these algorithms in the sense that the Diffie-Hellman key exchange algorithm is able to establish the common key K without actually exchanging the key, right? That's the beauty of these algorithms. Of course, the algorithm is not mentioned here. When you say combine key, it is nothing but the Diffie-Hellman algorithm that is working here, right? And remember, Diffie-Hellman algorithm is an asymmetric encryption algorithm. Now, of course, once you have this encryption, symmetric encryption key that is established, what Alice and Bob can do? Alice can create, the encrypted communication with the help of common key K. So once you have the common key, both of them, they can actually exchange the information in a secret manner using symmetric key encryption algorithm. So meaning you are solving key exchange problem of symmetric key encryption using asymmetric key. So asymmetric key algorithms are helpful in establishing the common key of symmetric key encryption algorithm. I hope these points are clear and then categorical and there are no doubts in that. In case if there are any doubts, please let me know. I'll pause for a second here and then I'll try to clarify. Okay, I think I'll continue. So next, is it this only encryption and decryption and key exchange only? Of course, certainly not. I said you have a fundamental goal of cryptography that is called authentication. So you have public key signatures which are coming from asymmetric key encryption algorithms, which are going to be used for signing the messages. And hence, one can verify who is the origin, from where the origin of this message is coming from. So if suppose Alice is sending a message to Bob, what Alice can do, Alice can sign the message using her private key, and everybody can verify whether it is sent by Alice or not by the help of Alice public key. So signing of the message is with the help of private key, and verification of the signature with the help of public key of the signer. So Alice is using her private key called actually KD, which we have discussed in the previous slides. Similarly, anybody can verify the signature with the help of Alice public key, which is KE. Right? So this is another example or use case of public key encryption algorithms. Right? So now these are all about the fundamentals. Now, what are the algorithms we have? The most popular algorithm we have in asymmetric systems is RSA algorithm, which is actually based on fundamentally rooted to a particular problem. Generally, what happens? We will have problems. We will try to find the solutions for it. If we have a solution, our problem is done. But RSA is based on a particular problem for which there is no solution at all so far. So it is based on a particular problem called finding the prime factors of a large number. There is no classical algorithm, or it is highly difficult to find the prime factors of a large number, which is basically a problem. Based on that problem, RSA is having its strength and hence was able to provide security to the communication. So I'll just quickly show you the algorithm. I'm not going to explain this, but if you notice, we are going to use two large prime numbers PQ and find its product. And from that, we are going to create a public key and private key. So fundamentally, we have chosen two large prime numbers PQ, and from which we have taken the product of these two prime numbers, and then we have taken the value n, which is the product of these two numbers. And then we have proceeded further in the algorithm, and finally we have created a public key called n comma e and a private key called d. As the name itself, private key, as the name itself is saying private key, this is kept confidential. And then as the name it is saying it is public, it is kept open. That means everybody knows. So this would be Alice public key. This would be Alice private key. The value d would be the private key of Alice, and the value n comma e, which will be kept open, is known to everybody, and hence it's the public key. Now in this algorithm, the encryption goes and decryption goes. I'm not going to deal with all that. But if you look at this algorithm, we have taken two prime numbers called PQ, and we have found out their product called N, and by multiplying P and Q, and we have taken an integer value called E by satisfying a particular condition, and we have also found the private key called KD, which is actually having some relation with the E. Now, these are the variables of this algorithm. Now, if you closely observe, I have kept n comma e as public, and if you see, d is private. Similarly, these two numbers, PQ prime numbers, are also kept private. When I say these two values are public, even attacker also knows these two values. But in order to calculate d from this particular n, what actually attacker requires is these two variables, which are prime numbers, two prime numbers. Now, from n, can the attacker will be able to calculate these two prime numbers? Of course he can, but if there is an algorithm. So far, there is no proper classical environment algorithm that allow somebody to calculate the prime factors of this particular n. So meaning what happens, if you have two numbers PQ, it is easy to calculate its product. But if we have its product n, it is becoming challenging to calculate PQ. So this is easy and this is difficult, right? Because number one, finding the factors, but finding the prime factors, and finding the prime factors of a number which is of, say, 300 digits. So typically we say 1024-bit algorithm. So 1024 means roughly it's about 300 plus digits. So finding such for finding prime factors for such a large number is computationally difficult. So take an example. Imagine if I increase that 1024-bit to say 2040-bit, 2048-bit, you see the number that what we are going to get. Suppose given this particular number, if somebody is asking you to find the prime factors of this number, this is computationally infeasible task for the current generation computers. So this is the challenge of the prime factorization on which RSA algorithm is built. So since this problem is not solved, people have built the encryption algorithms on top of these variables called N, E, D, and hence providing the security. Now, what happens with the current the quantum computers is we are able to crack that particular problem. So next we have the another crypto primitive called hash functions. So you provide the message to the hash function, it provides you a digest of the message. Again, hash functions are mainly meant for authentication purpose or for the signature purpose. Now you have one more cryptography primitive called digital certificates, which are mainly meant for identifying what is the actual public key of an Alice. Few minutes back, I said public key of a user would be known to everybody. When I say public key is known to everybody, how it is known in an authenticated manner. So suppose if I'm having my public key, how somebody would know what is my public key in an authenticated manner. And for that purpose, we have digital certificates, which provides authentication to the public key of each communicating party. So A, B, Alice and Bob, when they are interacting, Alice would get a digital certificate from the certificate authority, wherein which the certificate authority ensures the public key of Alice is authentic. Similarly, for Bob also, public key of Bob is getting authenticated by certificate authority in the form of certificate. Now onwards, if A wants to share his public key, rather A actually shares his certificate, her certificate. Similarly, Bob would share his certificate. This is what is the purpose of digital certificates. Now, if you look at our Windows operating system and then our folders and all that, you can see already these certificates are being available. Similarly, we have one more entity called signatures, wherein which when there is no trust between the sender and receiver, actually we said so far Alice and Bob are interacting and Eve is listening, meaning actually Alice and Bob trust each other and Eve is eavesdropping party. But actually imagine if there is a scenario wherein which Alice don't trust Bob, similarly Bob don't trust Alice. Whatever the message Alice sends to Bob, Bob asks her to sign and send it. So in such cases, we have digital signatures which are in place. Again, I have mentioned that digital signatures are supported by public key encryption schemes. You can see here, Alice is sending a message for which she signed that message with the help of Alice private key, and then of course, encryption is provided to provide the confidentiality, and then Bob would decrypt it. And you can see here, the receiver's public key is used for encryption purpose and the receiver's private key is used for the decryption purpose. But importantly here, if you see here, Alice has signed the message with her private key. Bob is verifying that signature with the help of Alice public key. This particular, this particular image gives you a beautiful illustration of usage of the asymmetric encryption algorithms in a different manner. You can see here, first, private key of Alice is used for signature purpose. Public key of Bob is used for encryption purpose. Similarly, for decryption purpose at the receiver side, receiver's private key, meaning Bob's private key, is used for decryption purpose, and for verification of the signatures, sender's public key is used. So this is senders, this is receivers, right? Now here you can see here, this is the receiver and then this is the sender. So meaning the keys, the KE and KD can be used in an interchangeable manner. That is the beauty of these keys. So we've said encryption, decryption, and then we have seen RSA algorithm, we have seen certificates, we have seen signatures. Now this brings a whole ball game of the cryptography, wherein which we have a symmetric encryption algorithms. Of course, our focus was not much on that, but we are focusing on asymmetric encryption algorithms, which are meant for number one, encryption and decryption purpose. Number two, for exchange of the symmetric keys. Number three is about exchange or establishment of the secret keys and so on. So we have also seen digital signatures, wherein which you can see that all these digital signature algorithms are essentially asymmetric algorithms. Now, this is what is the context now. When we say we are entering into the post-quantum cryptography, this is what is the context of cryptography. Now we are entering into all of us, we are hearing about developments that are happening in the quantum computing. People are talking about the realization of the quantum computers from the theory to the practice. Every company is claiming that they have achieved a quantum computer with so many qubits and all that. And people are saying that in a few years down the line of maybe 2 to 3 years, we may have a commercial quantum computers coming into picture. That is what actually the another side of story. Now, why actually there is a lot of buzz on the quantum computing? And of course, you have seen last 2-3 days of your lectures, the fundamentals of quantum computing in terms of qubits, Q-gates, quantum registers, quantum memory, then quantum circuits, all that, the fundamentals and math behind those aspects are also provided. Now, I'll just quickly highlight why these quantum computers are becoming more powerful and more challenging or more attractive towards certain problems which are not solvable by the classical computers. Number one, if you look at the quantum computers, they are going to deal with the complex numbers, wherein which in a classical computers, we are all dealing with the regular numbers of real numbers, wherein which quantum computers, you are going to deal with the complex numbers, right? Of course, a real number is also a complex number with a imaginary field of zero. Actually, quantum computers are dealing with the complex numbers. And then from single state environment, we are moving towards the superposition of state, meaning which given a 2-qubit system, you are going to have all possible states of the 2 qubits, meaning 4 at a time being available in the form of superposition of all 4 qubits. That is another beauty of the quantum computers that are making the quantum computers powerful. And also moving from locality to the non-locality algorithms, deterministic laws to the probabilistic laws, and then able to handle from certainty to the uncertainty computing, meaning probabilistic computing. So these are the fundamental features of quantum computing that are making quantum computers more powerful. Just to give you a picture of a glimpse of, if you look at, if you have 2 bits, you are going to have the states like 0, 0, 0, 1, 1, 0, and 1, 1. And these are all available sequentially. We do the calculations of different gates, logical gate operations that we use on these particular, this one. In case of quantum computers, we all know that these are not bits, rather they are qubits. And we are going to have, if a 2-qubit system, all possible 4 states of qubits would be available at a time to the user in the sense of quantum superposition. So that is where the quantum computers are being recognized as powerful, and hence we are going to have quantum speed up, right? Now, when you have such computers of quantum computers with high such powerful computations, now what happens with the cryptography algorithms that what we have discussed few minutes back? Now, all these algorithms, especially the prime factorization algorithm, right, or prime factorization problem, meaning if you have a number, we have said that when you have a 2 numbers PQ, finding n would be easy, but whereas, given an n, finding P and Q would be challenging. That's what is the fundamental challenge or problem on which RSA security is built upon. Now, with a quantum computer, we are able to provide solution to this particular problem. Similarly, discrete logarithm problem on which the Diffie-Hellman key exchange algorithm was working is also on certain mathematical problem called discrete logarithmic problem, for which we don't have a classical computer able to providing the solution. whereas quantum computers are able to provide the solution towards that. So all these mathematical problems are being cracked by these quantum computers. So how? It is with the help of a popular algorithm called Shor algorithm. In 1994, Peter Shor has showed that quantum computers can be leveraged to build the solution for finding the prime factorization problem. Now, if you observe, it is in the year 1994, meaning what? There were no quantum computers during that period and everything was only a theoretical. But then Shor has shown that an algorithm can solve this particular problem. But since there were no quantum computers, people were not worried about, especially people from cryptography and the security domains. They were not worried about the algorithm. But then now once we are hearing that quantum computers, the hardware is being realized, the software is also being leveraging this hardware, then people are realized that yes, now the time has come for realization of the Shor algorithm, right? Now, what is the Shor algorithm? It is the algorithm. It's essentially a quantum algorithm for integer factorization, and which can factor a composite number n in a polynomial time, especially breaking the RSA algorithm or even other public key crypto system algorithms, right? So what is this Shor algorithm actually is doing? It is actually how it is actually solving that particular problem is it is minimizing or rather actually translating that original problem into a different problem, right? So meaning what? The actual problem is to to find the factors of a large integer. That problem is being converted into a period finding problem. So it turns out that we can build an efficient quantum algorithm to find a number period such that you have a function f wherein which f over x plus but that particular period r, if you take, it will leads to f of x for any given function x. So Peter Shor has actually mapped the original problem to this period finding problem, where in which you are able to find the prime factors of an integer in a polynomial time. So what is that? Our aim is to find the prime factors of a number n. However, this can be related to another problem called finding the period r of the function, wherein which you are going to have the x values ranging from 0, 1, 2, and so on, to finding a period called r for this particular function called f of x over an is equal to a power x mod n, wherein which a is any randomly chosen positive integer and which is co-prime with n, meaning what? There is no common factors with the n, meaning GCD of n comma a is 1. Right? So finding this particular solution to this period finding problem is what actually Shor has done, and hence from which from this people have found the factors of the given number. So I just thought that I can take from some of my previous lecture notes what is actually this particular algorithm. So you can see that there are steps in this algorithm, starting from my actual number to be factored or finding the factors is the capital N. So that is my first step. And in the second step, I take a random integer k, and from then I'm going to proceed with my algorithm, wherein which I check whether my n and the chosen k value are co-prime, meaning if GCD is 1 or GCD is not 1. If GCD is not 1, then obviously whatever the value that I have chosen in step 2 is the factor. If not, I'm going for the next step. So if you observe here in the next step, the function that what we have mentioned in the previous slide, the same function is what actually I'm going to find, wherein which I'm going to calculate the period called R. What is the R? The R is all about the number of iterations that I'm going to make in this particular step. So the number of iterations that I'm going to make in this particular step indicate the period R. So finally, I proceed. If R is odd, again, I'll go to the step 2 and choose a different integer. If not, I'm going for the next step, wherein which, totally with the 7 steps, I'm going to find the factors, prime factors F1 and F2. So now fundamentally what actually we are going to do is how many number of times we are going to iterate is that R. So there is one example again. Generally when I take the session, I have used this example and then I have proceed. So you see here the n value what I have chosen is 357 and k value initially that what I have taken randomly as 52. And then when I proceed further, you can see my objective is to find R. So I have taken the variables. When I proceed further, you can see I have iterated for 6 number of times. And then when I proceed further, I'm able to find the prime factors, and then my period is R. So period finding is helping me to proceed further and finding the prime factors of the number. Now, this particular process of iterations is the one that goes to the quantum computer. When you look at the whole algorithm from the step 1 to 7 will not be executed by the quantum computer. Rather, this particular period finding would be dealt by the quantum computer. The reason is, if you observe here, the iterations from 0 to 6, meaning, I have actually made 6 iterations. This is my initial step. So totally 6 iterations for the given this particular simple case. This is 6 iterations. But imagine about, the number that I have shown, which is about 300 digit. You can think of number of iterations that would be required for a classical scenario. But we are talking that this is going to the quantum computer, and hence what happens when you put all these things in a superposition, iteration phases, what happens? All of them, they go at a time to the quantum computer to the qubits. So meaning in a single, instead of having 6 iterations, you will do in a single iteration, all these tasks can be computed. That is what is the beauty of the quantum computer. So for that purpose, of course, we need to go for quantum Fourier transformations for that particular step, because it is the QFT that makes all our input will be in a superposition state of all possible scenarios. So you need to implement quantum Fourier transform inside the Shor algorithm, and hence we proceed. I think this is the algorithm. I'll just skip it, in the interest of time. So all of us understood that the Shor algorithm is going to break the RSA algorithm because it is able to find the prime factors of any given number. Now, the point is, whatever we see here on the slides or maybe in some of the books, it is all about numbers of 2 digits or maybe, single digit or 2 digits. But then we are talking about large numbers. The quantum computers are able to crack it in a fraction of seconds. Then you have next algorithm called Grover's algorithm. What is the purpose of Grover algorithm is, of course, it is not directly impacting the asymmetric cryptosystems, but rather actually it is impacting symmetric cryptosystem. The reason is that it is going to perform unstructured search in a very less amount of time and even less number of steps. Meaning what? Imagine that your job is to find a phone number in an unsorted telephone directory. No, of course, you need, about n number of steps to get a particular right answer in a classical scenario. However, we can perform that particular search on that same unsorted telephone directory and identify the correct answer in a root n number of steps, which is a significant speed up in terms of computation. Oh, sorry. So, as I said, your any unsorted data search is very faster in terms of Grover algorithm, which takes only a square root of n number of search items, which is a substantial improvement in a search space. And hence what happened, this is the algorithm of Grover search algorithm. I'll just quickly give one example how this algorithm works rather than actually explaining the algorithm. Imagine that I have my an element, an array with about 10 elements which are unsorted. And my job is I wanted to find, whether a particular number is present. If it is present, probably, at which index location. So in an ideal worst case scenario, you need to, in a classical system, you need to perform 10 checks because you have n value here. It is 10 elements. So you have to perform 10 checks. Whereas in the case of Grover algorithm, Grover is going to perform this quantum search by keeping the superpositions of all 10 indices at a time. So I think in previous sessions, you must have heard about what is superposition. We are going to have for every index element, you are going to have, the certain probabilistic amplitudes which are defining, and hence you are going to keep every element in a superposition state. So if you see here, I have indices from index ranging from 0 to 9, and these are my elements. When you keep in a superposition state, of course, with the equal probabilistic amplitudes, I'm going to keep. This is my first step. So once I have done that, so what I'm going to do is that I'm going to assign a oracle function. Of course, in this case, the oracle function, what I'm going to do is I'm going to check if an index value has, in a particular index has the value 72, I'm going to return the value as true, the function value as true. Otherwise, if the value does not exist, I'm going to return as 0. So if you look at classical search, you are going to perform a sequential search over the all the array indices and then trying to find the 72. But whereas in the case of quantum, since we are going to keep this particular oracle function is deployed over the superposition of all the elements. Now what happens is that we are going to flip the sign of the amplitudes, which is, we call it as the flipping the amplitude values. And wherever this target index is identified the value 72, we are going to flip the amplitude value. So meaning in a single search, you are going to identify the element at which index that is available, corresponding amplitude, we are going to flip the sign of that particular amplitude, right? So next we proceed to conduct the diffusion operation called Grover's diffusion operation by computing the average amplitudes and reflecting that each average amplitude over the amplitude of all the indices. And this, I repeat this particular diffusion operation certain number of times, so that what happens, my amplitude values from all are the equal stages to different amplitudes, the amplitude values would vary. And especially you can notice that for that particular index at which I have identified the 72 value, the corresponding amplitude value will get maximized. Now the question generally naturally comes, sir, you have already identified 72 in the previous step. Why actually we are going, and then you can always say that, yes, we have identified, and then, you return value 1. Why actually I'm doing this averaging and then reflecting that amplitude values? Why I'm doing this particular step? The reason is simple. Now we are actually at, if you look at this particular step, we are actually at equal amplitudes. All of us must have learned from the previous sessions that when you have the superposition, you are going to have it in a superposition state of all states. But finally, when you want the result, you need to perform the measurement. Remember, in quantum computers, what is the output of the measurement is actually probabilistic. It depends upon the amplitude values. What would be the outcome of the measurement is depending on the amplitude values. But if you notice here, amplitude values are all same. So what I need to do, I need to increase the probabilistic amplitude value so that when I measure it, my outcome would be whatever is my desired index. So that is the reason why you are going to have this diffusion operation that is coming into picture. So you are going to increase the probabilistic amplitude value, and hence when you measure it, what you will get is, the index value 6. So that is where you are going to have the diffusion. And remember, this step may appear as an additional, but then what is the speed up that what you gain here is important, right? So identifying this particular, the index value through your superpositions is important. But don't think that, sir, I'm doing this, diffusion operation, which is increasing. But of course, this is only a, to make that measurement to, to get the highest probabilistic value, right? That is the algorithm steps. So these are all the how you are going to do the average and then reflecting that average across all probabilistic values. And finally, you get the index values 6. Now, this is what is the Grover algorithm is doing. But the question is, as you see here, in a classical case, to search over that array of 10 elements, you need 10 checks, whereas typically you need to do this diffusion operation just with the 3 iterations. You can finally get that index value 6, right? Which is a quadratic speed up. Now, what is the impact of this Grover algorithm in a security? So this is going to handle, or this is going to make our symmetric encryption algorithms are vulnerable. Meaning what? Imagine if I want to know, or if I want to break this common key K, I can perform a brute force search in a quadratic speed up with the help of Grover's algorithm. So 2 algorithms, whatever we discussed, the Shor algorithm is impacting our asymmetric algorithms, asymmetric encryption algorithms, and the Grover algorithm, which is speeding up the search operation, is impacting symmetric encryption algorithms. So this is the challenge of the 2 algorithms that what we have in quantum computer towards the cryptography that what we have. Now, that is the reason why we are going for post-quantum cryptography algorithms. So what is the post-quantum cryptography? It is about development of algorithms which are quantum resistant, public key algorithms. Meaning what? As I've said in the very beginning, how I am going to secure the communications from quantum threats. When I say quantum threats, what does it mean? The meaning, the threats coming from Shor algorithm as well as the Grover algorithm. Of course, the Grover algorithms we are not dealing much, because what I can do here is that I can actually increase the size of K, so that my search will be much more larger. Whereas our focus is actually on the Shor algorithm, or meaning asymmetric encryption algorithm. That's why the PQC algorithms are majorly focusing on quantum resistant public key algorithms, right? So what is happening with the PQC algorithms is we have multiple types of, or multiple variants of PQC algorithms in the literature. One is hash-based public post-quantum PQC algorithms. Then you have multivariate cryptography algorithms. Then we have code-based cryptography algorithms. Then we have lattice-based cryptography algorithms. Today, we actually deal with the lattice-based crypto algorithms and hash-based crypto algorithms. The reason, the NIST, whatever the NIST released standards that are in the last year, the 2 algorithms, those 2 algorithms are coming from these 2 types of algorithms. These 2 types of, the cryptography called lattice-based cryptography as well as hash-based cryptography, or hash-based signatures. Right? We will touch in the next few minutes about these 2 types of, or these 2 families of cryptography algorithms. Now, to proceed further, let us understand some background knowledge. Now, imagine I have a cube, and which has certain corners A to H, A to H. So these are all my corners. Now, when I have this cube like this, now you can also notice that there is a point. There is a point called small a. Now, the question what I have is, to which of the corners A to H, the point is closest? Whether this particular point is closest to this corner, or is it close to this corner, or this is close to this corner, or to which corner? If somebody asks this question, how do we answer this? Now, the answer, actually, to answer it, you need to actually assume certain things. Number one, if you notice, if I assume that this particular point is located inside the cube, then to which point, which corner this A would be closest. Similarly, if you assume that this particular point is placed on the front plane of the cube, meaning on the front side, meaning, this particular front side, if X or this particular point is placed here, is it close to D, or is it close to B, or is it close to A, or is it close to C? Or even, outside, meaning, this is outside of towards your side, towards this particular side, to where this is, to which corner it is closest. Similarly, no, it is not at the outside or to the front side, but rather it is actually the back side. A is at the back side, right? Then in such case, to which point this is closest? Now, how do I answer it? Given this particular problem, how do I answer this? Certainly, to answer this is a challenging task. Why? The reason is it is impossible for us to derive a single correct answer either by visual inspection or by the mathematical tools until unless you know some additional information, right? Until and unless we know some more details, it is very difficult to tell to which corner the given point is closest in a given cube. Why? The reason is, if you look at, actually, we are not seeing a 3D cube, rather actually we are looking at a 2D cube. Meaning what? The hardness of this particular problem that we are not able to tell to which corner this particular point is close, because since there is a dimensionality reduction, we are not able to answer. The reason is we have actually 3D cube, but we are actually looking at a 2D plane. So, and hence we are not able to precisely answer that particular problem. So dimensionality reduction is creating a problem. So if you see here, two important principles we need to understand from that particular diagram. Number one, there is loss of information. Okay. What is the loss of information? From 3D to 2D, when we make it, we are unable to uniquely identify the point's exact position due to projection of your 3D to 2D. Okay, so this is called loss of information. This is something unique now? Of course, certainly not. If you observe, few minutes back, I talked about the hash algorithms. What is that hash algorithms are doing? The hash algorithms are taking a larger input space and mapping it to a smaller output space, right? A fixed output space. So my input is always variable input. My input output is always fixed output. This is my output, which is fixed. So from a variable input, I'm mapping it to a fixed output is the job of hash function. There also you are going to have loss of information. Of course, there it is becoming the strength. The reason is attacker cannot take an output and create the original message, right? So this is the principle of loss of information. And also there is another important the principle called approximation. We created the problem of finding the corner element from the set that is nearest to the point A. So these two entities are related to concept of uncertainty. And especially these two schemes, one is loss of information, another one is approximation. These two principles are fundamental to the PQC schemes that what we are going to discuss, whether it is lattice-based cryptography, whether it is code-based cryptography, or whether it is a hash-based cryptography. These are the fundamental guiding principle. Now, if you look at what is lattice-based cryptography, so as I said, these are all rooted to this particular problem of loss of information and approximation. So the lattice-based cryptography start with giving the corners. You have the corners A to H, and we deal with several problems such as related to the corners and the intermediate points, and we are going to try to find out what is the closest vector or shortest vector problem. Addressing the closest vector or shortest vector problem is the lattice-based cryptography. So if you see the other family of PQC algorithms called code-based cryptography, wherein which these corners A to H are used as the code words of an error correcting code, and A is considered as a noisy variant of one of the code words, and you are going to find out to which particular corner this particular A is closest. Again, here you are addressing code-based cryptography. Again, the third one is about hash-based cryptography. We are dealing with the information loss. As I've already mentioned in the previous slide, you are fundamentally hashes itself is rooted to the information loss. So any PQC algorithms or family of algorithms, they are rooted to this particular foundation principle. Now, we'll deal with the first variant or first version of the PQC algorithms called lattice-based cryptography. So, but first of all, what is a lattice? So let us understand quickly about some math. Basically, a lattice is a set of points, and these points are in an n-dimensional space, and you can observe that these points are having a particular periodic structure, and that particular periodic structure gives the name called lattice. Of course, if you look at the the algebraic structures where you are going to have partial ordering structures called lattices, that is different. But here what we are talking about, the geometric n-dimensional space period structure called lattices, that is different, right? So now here, if you notice how I actually going to precisely define a lattice is defined as some set of integer combinations of independent vectors. Imagine I have n number of vectors a1 to an, and these are all called basis vectors. Meaning what? From these vectors you can derive other things, and each of these basis vectors are also going to have the integer coefficients, and I'm going to represent that lattice L as, if I have n basis vectors, each basis vector is going to have a linear integer coefficient. So you are going to have n coefficients, x1 a1, x2 a2, and so on, xn an. This I'm going to call it as a lattice structure. If you notice, each of these basis vectors a1 to an, each vector is having a dimension m, and the vectors forms m-dimensional space, right? Each vector is of m dimensions, and hence your lattice is of m dimensions. Okay, and of course here, if you notice, there are n number of such vectors a1 to an. There are n number of such basis vectors, and hence rank of this lattice is n. So the total number of vectors defines the rank of the lattice. Each vector is having m number of dimensions, which also defines dimension of the lattice space. So these two variables we need to remember. Now, let us take several basis vectors. Say, take an example, I have n basis vectors. And from where these basis vectors are coming? These basis vectors are coming from an integer set. Okay, I'm calling that integer set as Z, and of course I'm going to call it as ZQ. The reason is I'm going to take an integer set of any set of integers of range 0 to say 16, 0 to 17, or whatever it is. Now I'm going to have these, each of these basis vectors are having m number of dimensions, and hence my lattice dimension is m. So this is my lattice. And then what I'm going to do is these basis vectors are having integer coefficients s1, s2, so on. Since I have n number of basis vectors, I am going to have n number of coefficients, right? So s1a1 plus s2a2, so on, snaa. All this is going to give me a particular point on the lattice structure called T, which is called a target point. So now if you closely observe, I have n basis vectors and I have n integer coefficients. These are making me, or these are taking me to another target point on the lattice structures, because obviously these are all the basis vectors. When I multiply them each with their coefficients, what I'm going to get is another point on the lattice called T, which is a target point. Now, this is the fundamental. Now, what is the job of an adversary? An adversary is now given the starting point, meaning all these basis vectors a1 to an, and also adversary is given with the target point T. Now he is asked to find, he has the basis vectors a1 to an. He has the target point t, but what he was asked to find is what are these values of the integer coefficients s1 to sn, for which he has to multiply the starting point so that he can reach the ending point of t. Now, the job of adversary is to find the secret coefficients s1 to sn. How do you generalize this problem? A dot s is equal to t, where in which I have my basis vectors given in the matrix form A, and my final target point, which is given in the form of a vector t. Now, the job of attacker is, or an adversary is, to find this particular secret coefficients s. So this is called A dot s is equal to t. This is the problem. Can this problem be solved? Of course, this problem can be solved as such with the help of, the problem can be solved with the help of Gaussian elimination. Now, there is a simple example. If you look at, I have taken the integer set 17, and I'm going to take rank of the lattice as 4, meaning I have taken 4 basis vectors, right? Each basis vector is having 7 dimensions, so, and hence my lattice is of dimension 7, because each basis vector is of having 7 dimensions. Now I'm going to represent that lattice structure as Z17 power 7 cross 4, where in which the 7 is the dimension, 4 is the rank. And of course, I can perform transpose operation also. This is my lattice. Now, what is my job? I have this the lattice structure in the form of a matrix, and also I have target point given t. Now, so A dot, this is A, this is S, this is T. Now, when A, T are given, the task is to find the coefficient vector S1, S2, S3, S4, which is the secret coefficients. This can be easily calculated with the help of Gaussian elimination, as I said. So the secret vector can be easily found out by the adversary with the help of Gaussian elimination. Now, so why we are discussing this? We are discussing this because as such, this particular problem, A dot S is equal to T, can be easily be cracked. But how do I make it? This is a non-trivial problem. So for that purpose, we take T not as a point on the lattice, right? So in the previous scenario, A dot S is equal to T is a point on the lattice. If you see here, T is the point on the lattice, but now we are going to take the point not on the lattice, but as a point close to a point on the lattice, right? So this is the tweak we are going to do. How do I am going to do it? So for that purpose, I'm going to refine that expression A dot S is equal to T as A dot S plus E is equal to T dash, where this is my error. This is my error. If you look at here, LWE stands for learning with errors. So this is a category of problem called learning with errors. I have tweaked my problem of A dot S is equal to T as A dot S plus E is equal to T dash. Now this T dash is not on the lattice structure, whereas this is on the lattice structure, right? And this is something close to the lattice structure, a point on the lattice structure. Now, if you see here, how my problem gets transformed, this is my A, this is my secret coefficient, this is my error vector, and this is my target vector. And this would be known to the adversary, and this would be known to the adversary, and whereas these two would be not known to the adversary. And remember, in everywhere you can see that we are performing these operations at mod 17, right? Now, so without providing E or S, an attacker will not be able to compute the correct solution, since T dash is not a point on the lattice structure. So there is a you can compare both these problems. So A dot S is equal to T, and this is A dot S plus E is equal to T dash. So if you notice, the target vectors t and t dash are, if you notice, they are very close to each other. Meaning you can see here, this is t, this is t dash. You can see here, they are very close. The elements are very close. Either +1 or either -1, or maybe they may be a 0, right? So meaning, the error values would be ranging from, a -1, 0, 1. But with this small error, the problem is becoming non-trivial, rather it is becoming tougher, right? So of course, the E vector is already given here. This is your E vector. What we have this one. So you can notice with a simple small error values, the trivial problem is becoming a non-trivial problem. So these problems are regarded as problems that even the quantum computers are not in a position to crack. So in summary, we can say that introduction of an error vector. Of course, remember what we have discussed here is a simple scenario, but in real world, we deal with a large set of matrices and values. Now, in summary, what we can conclude that introduction of the error vector can achieve certain goals. Number one, the standard techniques such as Gaussian elimination, you cannot recover the secret coefficient values, and also we can also make sure that the brute force approaches also do not track this particular problem. So for that purpose, we need to choose carefully the dimension m value and the rank n value of the lattice structure. Remember the example what we have seen is a simple a dimension of m, which is 7, and the rank of 4. It's a very simple lattice structure. So solving such problems are indeed hard, and which are belonging to a class of NP-complete problems, and these are even harder for the quantum computers. Meaning what? PQC algorithms are looking for problems that are not solvable by quantum computers. If you look at RSA algorithm, which was based on finding the prime factors, a problem that classical computers were not able to solve, the quantum computers are dealing or finding it hard to solve certain class of problems for which the large scale quantum computers, they are finding it hard. So the PQC algorithms are fundamentally based on those problems. Now, from this particular discussion, whatever we have done, there is a formalization of what is LWE problem, where in which you are having this set of basis vectors which are represented in the form of a matrix. Of course, we are calling it as the lattice, and the problem is to determine the set of secret coefficients given an error. A dot S plus E is congruent to T at mod Q. Remember in the previous, that mod is the Q value is 70, right? So this is the learning with error problem. So based on that, we are having, of course, I'm skipping this encoding and decoding. Those who are interested, they can check it. Why we have to do, before going into encryption and decryption, we need to do encoding and decoding. The reason is that you are having to have messages. What we are going to, in our plain communication, what we are going to have is an n-bit message, which are nothing but in the form of zeros and ones. They need to be mapped to the elements of the integer set, what we have considered for the lattice structure. And for that purpose, one has to perform encoding and decoding, but that is not the primary focus of the PQC. We can discuss, or we can check it online. What is this encoding and decoding? So I'll skip it. So essentially, when you say encoding, we are going to take the sequence of bit string and then map it to the integers of set of the lattice structure. Now there is an key generation algorithm based upon the LWE problem what we have discussed. This is called simple learning with error key generation algorithm, where in which we are going to generate, with the help of this particular algorithm, the public key, where in which you can see here, public key contains the target vector, or that what we have discussed, A dot S is equal to A dot S plus E is equal to T. If you see, the public key component is the lattice structure and the target vector T. Now, what is my secret, or what is my decryption or secret key? The secret key is nothing but set of secret coefficients. So your key generation algorithm is going to take the target and the lattice structure as public and the secret coefficients as the secret, meaning any attacker who wants to crack it or finding the private key, the attacker has to solve this particular problem of T is equal to A dot S plus E. So if you observe, T is openly available, A is openly available, the set of secret coefficients are not available, and of course error terms are not available. And remember, error terms what we have introduced is are very, very minimal. But with that, attacker is not able to find what is that S, even with the quantum computers. Now you have key generation, and once after that you have encryption algorithm with the help of learning with errors, and you are going to encrypt each bit by bit only that is possible. Meaning what? We take the single bit and then map it in the form of encoding and map it to the Z17 or ZQ, whatever we have integer set, and then over that we are going to perform encryption operation. Remember, this in particular encryption operation is close to the Elgamal algorithm that what we have in the public key schemes in a classical literature. You can see here the decryption, sorry, the ciphertext that what you get as an output of the encryption are two variables, right? Auxiliary variable as well as the actual cipher variable, which is close to a kind of Elgamal algorithm, wherein which one variable would be used to know the other variable during the decryption process, right? So this is about encryption. And of course, you are going to have the decryption. If you notice the decryption, you take the ciphertext values of the encryption and then perform the decryption. And then this gives you the decryption, the actual message. And since already we have done encoding, this is the reverse process of decoding, which you need to do, which is the reverse process of encoding to get the original message back. Remember, this is about learning with errors, encryption and decryption algorithms. Remember, the message that what you get output is simply in the bits, either 0 or 1. That is the one of the fundamental challenge with the LWE algorithm, simple LWE algorithm. And because of that, researchers have gone ahead and then proposed next set of algorithms called ring learning with errors problem, wherein which the lattice structures of matrices are replaced with the ring structures. Again, what is a ring here? Which is nothing but the algebraic structure of, I think, we all know about the set, the sets, groups, rings, and fields. So this is this particular algebraic structure, which is the rings and represented in the form of polynomials, right? So this is learning with errors problem. Again, has some key generation algorithms, encryption algorithms, and as well as the decryption algorithms. But in order to make it practical, what actually the NIST has released is a combination of simple as well as ring learning with errors. The combination is called module learning with errors. If you see here, the lattice structure, you can see which is in the form of matrix, but inside the matrices, inside the matrix, the elements are the polynomials. So module learning with errors is a combination of standard LWE algorithm as well as ring learning with errors algorithm is a combination of both, which is called module learning with errors algorithm. So based on this particular, we are having now current standards of PQC algorithm called Kyber 512, Kyber 768, Kyber 1024. You can see they are module learning with errors type of algorithms. So the current algorithm or current name or current protocol or the scheme, what we have is Kyber, but basically it is rooted to a family called learning with error, especially module learning with error. And that provides equivalent security to similar to our symmetric encryption algorithms, which is AES. So the moment you increase, of course, you can also see the increase in the key sizes of the algorithms. So of course, like this, there are various other algorithms, New Hope, product co-EM. These are all based on different learning with errors families, but essentially what is there standardized by the NIST is the Kyber algorithms, Kyber family of this one. So this is about one of the family of algorithms called lattice-based cryptography. Next interesting aspect or next interesting family is called hash-based cryptography, wherein which this scheme of algorithms are fundamentally rooted to Merkle tree of hashes. I think I heard in the previous sessions, you are having a session on blockchain, wherein which I know the speaker must have introduced you about the Merkle trees. Let us see what is a Merkle tree quickly. It's a basically a tree of hashes, Merkle tree of hashes. If you notice, at the leaf nodes, you are going to have the data elements. At the next above level, you are going to create hash of each data item. So data 1 and its hash, data 2, its hash, data element 3, its hash, data element 4 and its hash. And in the next level, you are going to have hash of these two hashes as created as the next level hash. So hash 1, hash 2 combinedly and creating hash of it, creating hash 112. Similarly, these two are combined and created a new hash called hash 34. And again, these two data elements again combined and created the final hash called hash 1234. This is your root hash. This is how a Merkle tree looks, and you are going to have a tree of hashes. Why we discuss it? Why we discuss in terms of PQC algorithms. The reason is the hash-based cryptography algorithms are helpful for digital signatures. Now, for digital signature purpose, earlier we said we were relying upon classical public key cryptography algorithms like the say RSA based or Diffie-Hellman algorithm, etc. and etc. But now, instead of those public key algorithms for digital signatures, we can go for hash-based signature algorithms. How we go for it? Let us say that I'm going to have say I'm going to have my again one key for decryption or one key for secret purpose, meaning secret key, K secret, K public, right? So what I'm going to have is at my leaves, I'm going to have my secret keys. So let us imagine I have two secret keys, P1, P2. What I'm going to do is from these two secret keys, I'm going to create a hash of it. And then again, another secrets, P3, P4, P5, P6, P7, and then P8. Imagine I have totally 8 such secret keys. Now, what I'm going to do is I'm going to create hashes of them in the form of Merkle tree of hashes, right? So I'm going to find first hash of each secret, combine hashes, and create a root hash. Now, this particular root hash, I'm going to keep it as the public key or verification key. Anybody wants to verify it, they can verify with the help of the verification key, which is the root hash and also the path. Imagine I wanted to verify a particular key, I need to give path of that particular key. I will not reveal the key, but rather I will give path of that particular key. That is the beauty of the hash-based cryptography. So let us see with the example. So as I said, we take hash of the keys and then build the Merkle tree structure. So I have say take an example. Earlier I said 8 keys. Now let us take 4 keys. So key 1, key 2, key 3, key 4. So I'm going to create hash of the key 1, hash of the key 2, hash of the key 3, and hash of the key 4. Now combine them like this and create the root hash, right? Now what I'm going to do is the sender uses any one of the secret key. So these are my secret keys. If I want to sign, I can use any one of the secret key to sign the message. Now I sign the message. Whoever wants to verify it, they can verify my signature. How they can verify? If I am sending my signature along with authentication path, and hence they will be able to verify. So take an example. If I am having my signature with the help of this particular key, third key. So what I'm going to do is I'm going to provide my signature signed document along with the root key and also the path. Meaning what? I'm going to provide my hash of the key with which I have signed, and I'm going to provide hash of 4 and then hash of 3, 4, and then the root hash, of course, the hash of 1, 2. Now, anybody wants to verify, they can very well verify whether I have signed with the help of key 3 or not by tracking it back, because I am providing the path in the terms of I'm giving hash 3, I'm also giving hash 4. Anybody can create hash of 3, 4, and then create the root hash, and then hence, the public key can be verified easily, right? But remember, I'm not going to reveal any of these keys. So because of that, later when I want to sign another key, another message, of course I can use key 4 or I can use key 1, because I have not revealed the keys. Rather, I have actually revealed only the hashes. And remember, hashes are nothing but one-way functions. Meaning what? You can do this activity. Given a input, you can always find the hash. But remember, with the hash, nobody can find the input to the hash function. That's what is the one-way function, right? So hash-based cryptography is based on this particular Merkle root of hashes, providing the users to sign over the documents and performing the digital signatures. So remember, for the digital signatures, we were saying that we are using public key crypto systems which are vulnerable to the quantum algorithms such as Shor, and because of the hash-based schemes, this comes under the family of PQC algorithms. We are able to solve the digital signature problem. So remember, lattice-based cryptography is solving your fundamental problem of PQ, the quantum asymmetric crypto algorithms. The hash-based cryptography is solving your digital signature problem, right? So whatever we discussed so far are about the PQC. Now, what the next scheme or next topic we are going to discuss is quantum cryptography, right? I have already mentioned in the very beginning, the quantum cryptography is all about how I leverage the principles of quantum computing to solve or to strengthen my communication. So one of the interesting communication aspect is the key distribution problem. What is the key distribution? As I said, if two communicating parties want to communicate in a secret manner using symmetric encryption algorithms, they require common key K. And for that purpose only, we were actually looking at asymmetric crypto systems which are vulnerable to the quantum computers. Now, researchers have decided whether quantum computing principles, whether they can be leveraged so that the key can be established secretly between Alice and Bob, so that they can communicate using symmetric encryption algorithm. So this is called key distribution problem. And for that purpose, I'll just quickly go to the actual distribution phase, wherein which both the communicating parties, Alice and Bob, they would be interacting in two channels. One is a quantum channel, another one is the classical regular public channel. Meaning what? You need to have a quantum channel in order to perform quantum key distribution. How this quantum channel would come? Of course, if you have quantum computing or quantum mechanic principles, if you have, then you can establish the quantum channel. So establishing the quantum channel is important for quantum key distribution, meaning we are leveraging the principles and properties of quantum computing for exchange of the symmetric key. And of course, it is not only the quantum channel, we also need a classical public channel, which can be even an untrusted channel, that is fine, right? So now if you notice, they actually exchange some pieces of information in both these channels, and let us see how it is. And I'm going to skip this particular polarization of photons. I'm assuming that this would have been covered in the fundamentals that we were discussed in the previous sessions, wherein which you are going to have, there are two types of polarization angles which would be considered in this key distribution scenario. That polarization angles we are saying called rectilinear. That polarization we are calling it as rectilinear polarization and diagonal polarization. Meaning what? Actually, I'm going to send the polarized photons in a communication channel, which is the quantum channel. This is the quantum channel. And you can notice these photons are being communicated. Now, these photons represent whatever the bits that I wanted to share with my receiver. So imagine I have two types of bits, obviously 0 and 1. So I can use any one of these two angles, a rectilinear angle or a diagonal angle. If I want to share 0, I can use a rectilinear angle or a diagonal angle. I can use rectilinear angle for 1 and diagonal angle for 1. So both these angles I can use and send the bits from sender to the receiver. Remember, these selection of these angles or selection of the basis, rectilinear basis or diagonal basis, is done randomly from the sender side. Similarly, the receiver also uses these basis, either rectilinear basis or diagonal basis, randomly. Sender is also sending randomly, receiver is also receiving randomly. Now the question is, how do you remove this randomness? Now you can see here. Now sender action. You can see here the sender. You can see here the sender first sending 0, and for that purpose the sender is using the diagonal basis, and obviously the diagonal basis, when bit 0 is sent, it goes in a direction given in a angle like this, 45-degree angle. So you can see that it is going in the 45-degree angle. As I said, receiver also uses the basis. What is the basis the receiver has used? He has used vertical basis instead of diagonal basis, meaning rectilinear basis. When once the receiver uses a different base, obviously for 0, what is the angle that at which the receiver would get is so you can see that received result is in the form of a horizontal, and hence the bit is 1, right? Next, sender is sending 0, and for that purpose the basis is used is the horizontal and vertical, and then obviously the transmitted information is the vertical, and the basis that is used by the receiver is also the same basis, and hence you can see that the received bit is same, and it goes like this. But now if you see here, the transmission basis and the between sending basis and the receiving basis are selected randomly. Neither the sender nor the receiver knows on each side what basis is used, right? sender is used as a different basis randomly, and then the receiver has used different basis randomly. But how do they conclude which basis they have used? And for that purpose, they refer this is happening in a quantum channel, and then now they go to the classical channel and ask each other, hey, look, I have sent the first bit with the basis of rectilinear or a diagonal. So my basis is diagonal. So which basis which basis the receiver has used? The sender will ask. If both are agreeing that yes, I have used the same basis, they will keep that bit. If both agree that they have used a different basis, they will discard the bit. So now look at here. In the case of first bit, both have agreed that they have used the different basis, and hence their basis is not matching, and they will discard the bit. Now, if you look at the second bit, both have agreed that they have used the same basis, and then they will use that particular bit as the key bit. Now look at the third one. Bases are different, so they agreed that they have not used the same basis, and they discard that particular bit, and goes on, right? So finally, when the transmission of bits, now in this case there are about 9 bits were transmitted, and among them, finally, when it comes to the key length, you can see that 1, 2, 3, 4, and 5. You have about a 5-bit key is established between sender and receiver, right? Though there are 9 bits are exchanged, actually 5 bits are retained. Meaning, imagine that I wanted to establish, say about 1024-bit key. You can imagine number of the bits that are needed to be shared, so that there may be an agreement or of the basis, there may be agreement of different in the basis, and hence you have to drop it. So consider only those bits for which the basis is matching, right? So roughly you may have to send about double of the bits that are need to be established. Meaning, if you have to send 100, you have to establish about 100 bits key, then you may have to send about 150 bit to be exchanged between Alice and receiver, Alice and Bob, or sender and receiver. As I said, this communication happens in the quantum channel, and agreement over the basis happens in the classical channel. Now, even if the eavesdropper attacker listened to the communication, the attacker would not know what are the bits actually shared. Attacker would know what are the bases, whether it is rectilinear basis or the horizontal basis, horizontal and vertical basis, diagonal basis or a rectilinear basis. You may know about the basis, but not about the bits. That is the beauty of the quantum key distribution. And now what I narrated is only a BB84 protocol, wherein which you are going to share the information in the form of bits. After that, we have other variants called BB91 and other protocols. So finally, when we proceed, the PQC algorithms, whatever I said, they are already being implemented and established in various cryptography protocols. What I'm showing here is about the TLS handshake. All of us know that in our day-to-day communication, we depend on HTTPS protocol, which providing us secured communication, and background of or backbone of HTTPS is the transport layer security, and wherein which all of us know that TLS popular handshake is there, in which the TLS handshake has exchange of the cryptographic primitives and then establishment of the keys. Now, the TLS is going to have the PQC version of TLS. So there are recommendations about what type of impact of quantum computing on the various existing cryptography algorithms. If you notice, the AES is the popular symmetric key encryption algorithm, which is going to be impacted by the Grover's algorithm, and hence, you are going to have larger key sizes for the AES. In case of popular RSA algorithm, this is no longer secure, and we require, the PQC algorithms that what we have discussed, right? So the US-based NIST has given the timeline of migrating towards the PQC algorithms, wherein which you can notice that now, as per this particular timeline, the NIST is releasing the standards during this particular period, and it is expected that by 2035 there would be universal quantum computers by which the existing the public key cryptography algorithms need to be completely replaced. So a few minutes back, I talked about the NIST released PQC standards. You can see that there are 3 standards released by NIST during 2024. Among the 3 standards, we are having algorithms called Crystal Kyber, which is basically a lattice-based cryptography algorithm, what we have discussed a few minutes back. And it is mainly meant for quantum secure key exchange algorithms, and it is going to replace existing the public key cryptography algorithms such as RSA, elliptic curve, and etc. Then we are having a crystals dilithium algorithm, again, which is a lattice-based cryptographic algorithm, and its purpose is to protect the digital signatures, right? Then again, for the digital signatures, we are, as I said, about the hash-based algorithms called Sphinx Plus, which is hash-based algorithm for the digital signatures. So in the existing, as of now, as per the NIST standards, the lattice-based cryptography algorithms that what we have discussed today and the hash-based the signature standards what we have discussed today are the currently available standards, and using which now the people are building protocols and products as per this. So all the existing cryptography infrastructure need to be migrated, especially to mitigate the attack of harvest now and decrypt later attack, wherein which attackers are, since as of now quantum computers are not readily available to break RSA algorithm and make any kind of a financial transactions happening or a secure or privacy preserving transactions that are happening insecure. As of now, no. But what attackers can do is they can do harvest now, meaning they can collect all these secure data which may be broken later point of time when the quantum computers are available. So we need to mitigate that particular attack, and hence you need to immediately actually migrate it to the current PQC standards, right? So compared to the QKD, PQC is much more important now, and of course it is less costly, because for a quantum key distribution you require quantum computing principles and then need to have devices and getting ready, establishing the quantum communication channels and all that. But PQC are less costly, and then you are already having the standards, right? So these are the NIST recommendations. Go for a symmetric encryption. Go for AES 256. If it is a stream encryption algorithms, you can go for ChaCha20 with 256-bit key. When it comes to asymmetric, you can see go for Crystal Kyber, or for signatures, go for Crystal Dilithium. This is what is the current recommendations, and how they are going to be implemented or migrated. Of course, in the form of hybrid encryption, wherein which your classical key establishment is already going to be there, and on top of that, you can have PQC algorithms being implemented, so that if you want one layer of security or a 2-layer of security, you can have. But always you can have the classical establishment. The reason is of suggesting to have this hybrid. Though there is a standard, people are little skeptical about the standardization of the security of the PQC algorithms, right? So that is what people are. Of course, they are testing and releasing, but still, for a safer side, they wanted to keep this classical and as well as go for the next layers of quantum safe algorithms from PQC. Of course, same also for the signatures, encryption as well as the signatures. You can see here, you are going to have regular classical algorithms signatures and also quantum safe algorithms. So first sign with the quantum safe algorithms, and then on top of that, sign with the help of classical algorithms, right? This is for the signatures. So if you look at the roadmap, on the short term, we are going to have, the PQC playing the major role. And on the longer time down the line, we may have, the quantum cryptography coming into picture if once we have a successful launch of quantum communication channels. In terms of our lab and then our communications, our team is working from quite some time on various aspects of quantum computing, quantum machine learning, and also quantum security, PQC and all. I just wanted to give quickly about some of our works dealing with the quantum computing, quantum machine learning. So you can see some of our works published in reputed journals on various aspects of quantum computing, dealing with models of quantum cognition and cognitive paradoxes with the contextuality, introducing the contextuality, and then quantum inspired models, wherein which we have built a quantum inspired ensemble approach for multi-attribute and multi-agent decision making. And also we have worked on quantum machine learning algorithms for various applications, right? So, this is about quantum security, especially on homomorphic encryption, taking the homomorphic encryption to the quantum fully homomorphic encryption schemes. These are some of the works that are published, and of course, our team is working with on different other problems. In this regard, those who are really interested, I would invite those who are all interested. They can freely interact with us. They can, we are ready to have, fruitful interactions for the benefit of all of us. The country is aiming to make a leading nation in the area of quantum computing. Government always says that we have missed the bus of semiconductors, but we should not lag behind in the area of quantum computing. And in that regard, we welcome all of you who are interested in these areas, whether it is machine learning, quantum machine learning, or quantum cryptography, post-quantum cryptography algorithms. We are ready to discuss and then, collaborate. So, these are some of the references that I have referred for the slides, and, you can also look at them. So thank you very much for your patient listening. And then if any kind of doubts you have, I'm happy to clarify.
Dear participants, if you have any questions, please raise your questions.
Please, sir, you can. My suggestion is give it in the chat window, because I'm seeing some noise in my speaker.
Meanwhile, I'm requesting all the participants, please switch on your camera for a while.
I would really request you to type it in the chat window, because I'm not able to hear anything. I'm sorry, my speaker is making some noise. Any doubts or any thoughts?
Okay. Any questions from participant side, please? Sir is waiting for answering questions. Okay. Sir, one question is there. Sir, your voice is not audible, sir. Sir, your voice is not audible.
Okay, I'm sorry that I'm in mute. Okay, so with regard to photons, the photons are used for the exchange of the information. The qubits that what are shared between sender and receiver, they are actually sent in the form of encoded polarized photons. So in order to exchange this particular qubit values, the zeros and ones, the polarization of photons are used. That is the purpose of that. And in fact, interestingly, this is one area where in which, you can see that, the role of the clear role of physics, the clear role of mathematics, clear role of computing, clear role of, the all quantum mechanics or maybe quantum sensing, all these disciplines come together. This is one of the beautiful area, right? Any other doubts if you have?
Now I'm requesting Vandana madam for gratitude note.
Thank you, sir.
Yes, madam.
On behalf of IT department, GMR IT, and Vardhaman College of Engineering, I would like to express our sincere gratitude for sharing your time, expertise, and insights for your FTP. Your presentation of today's topic, post quantum cryptography, was both informative and inspiring, and it greatly enriched our understanding of the subject. Your expert knowledge, clear explanation, and research perspective have greatly enriched the participants' understanding of the subject. Your contribution has truly added immense value to this FDP and inspired meaningful discussions and learning among all attendees. We deeply appreciate the time and effort you devoted to preparing and delivering such a thought provoking session. We look forward for future opportunities to collaborate with you again, sir. Thank you once again for being an integral part of this program. Thank you very much.
Thank you so much, sir. Thank you all the
Thank you.
participants.
Thank you all.
Yes,
I
sir.
think, yeah. Thank you.
Yes, sir. Yes,
Shall
sir.
I
Yes, sir.
stop sharing and then leave?
Yes, sir.
Think,
Yes, sir. Please stop.